Okay, here's the helper video for slope fields and Euler's method in Desmos. I'm starting on slide 3. Most people did pretty good on slide 3, but in case you were having a hard time, I thought I'd better start here. So sketch a solution curve that passes through the point 1, 0. So we're going to start by putting on a point at 1, 0. There it is. And now I'm going to follow the slope. So you can kind of think of this as like a dot to dot with the little lines pointing in the direction you need to move. So I'm going to follow this. I'm going to follow this slope until I reach a different slope. So then when I reach this slope, I'm going to follow that slope. Boy, this is hard to do. And then I'm going to keep going along that slope until I reach another slope. Boy, this is really shaky. And then I follow that slope until I reach another slope that changes it. There it is going that way. And then, of course, I can go the other direction as well. So I follow the slope that I'm starting on. And when I hit another slope, I go with it until I come to the next slope, and I go with that. And I go with that until I hit the next slope. There really should be, you can't see them because they're on the vertical axis, but there should be little slope markers on here that are vertical, but you can't see them because they're on top of the y-axis. All right, so there it is. As you can see, I'm following along the little slope marks, and when I hit a new one, it changes my direction. It also kind of reminds me of a pinball machine, where if your ball hits the side of the pinball, it changes its direction. All right, based on your sketch, make an educated guess as to the limit of f of x as x goes to infinity. So remember, f of x means y. So what is y going to be as x gets larger and larger? So think about this. What is happening to all of these little slopes? They're all getting flatter and flatter. See how over here on the left, they start really steep. But as we go to the right, they're getting flatter and flatter. So chances are it looks like it's probably going to end up going somewhat horizontal. And I would say maybe around 1.3, maybe 1.3. Yeah, I would say that as that f of x is going to probably go to maybe 1.3, something like that. 1.3, maybe 1.5. Just guessing. Okay, make an educated guess as to the limit of f of x, in other words, y, what's going to happen to y, as x goes to 0 from the right. Okay, so if I'm going towards 0 from the right, not from the left, from the right, following my line, notice these slopes, they were getting steeper and steeper, and again, they didn't give us enough little slope marks on the vertical axis, but it looks to me like it's going to get completely vertical. So what's the limit? What's going to happen to my y values? They're just going to keep going down, 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 down. So my f of x is going to be equal to negative infinity. Do I have an infinity symbol here? Let's see if I have an infinity symbol. I don't know. I know I saw some of you write an infinity in there, but I don't know where you got it from. So I'm just going to write the word infinity. Okay. Oh, look, there it is. It knows how to do it. Okay. Very good. So that's that one. All right. Moving on to slide 4. Euler's method with a step size of 1. Okay. Starting at the point 1, 0. Here it is. Point 1, 0. Call this point x0, y0, and mark it with a dot. So I marked it with a dot. Using the differential equation, dy dx equals 1 over x, find the slope at this point. Okay, so the slope, dy dx, is equal to 1 over the x value. Well, what's the x value here? The x value is 1. So I'm going to have 1 over 1. And so that is my slope, which is equal to 1. Right, so if you wanted to write m equals 1 or just put in 1, that's fine. Anything is fine. Okay, so the slope here, if I were to put in my little slope marker, like on our slope fields, I would have a slope of 1. Okay, so I'm going to submit that. This value is the slope of the tangent line to the solution curve at the point 1, 0. If you travel to the right along this travel line for a horizontal distance of 1 unit, at what point in the xy plane do you end up? Okay, so I'm going to have a slope of 1. I'm going to go ahead and just draw in. Look like that. A slope of 1 means up 1 over 1, right? Or I'm going to go up 1 every step. That's what a slope of 1 means. I'm going up 1 for every step to the right that I take. And then it says, what if I travel 1 horizontal distance to the right? So I'm going over 1. That means I'm going to end up going up 1. So there's my next point right there. And that will be x1, y2. Okay, and so notice the value of x is 2, and the value of y is going to be 1. So that would be at 2, 1. And I marked it with a dot. So at this point, you should have 2 plotted points on the graph. Yeah, that's it. That's all we had to do on 4. Okay, number 5. Notice they show us what we should have had on number 4. So if you got number 4 wrong, you'd know, oh, that's what I should have had on number 4. Now, compute the slope at the new point. Okay, so now I'm here at x1, y1, and I want to find the slope. So remember, our formula for the slope is 1, let's see if I can write on here, 1 over x. So you got to keep this in mind. We're using the same differential equation each time. The derivative, dy dx, is equal to 1 over x. So the slope is equal to 1 over x. Well, x here is 2, so it's going to be 1 over 2 is going to be my slope. So from here moving forward, I'm not going to have a slope of 1. I'm going to have a slope of 1/2. Okay, so remember slope, it means I'm going to go up half a unit for every 1 unit I go to the right. Okay, this is the rate of change is for every unit I go to the right, I'm going to go up half a unit. So that would take me to right here. Okay, so every step that I take, I'm going to go up half a unit. And so that's where my x2, y2 would be. Okay, so here's my x2, y2. So we're going to repeat it again because this is x2, y2, and I want to get to x3, y3. So now I have to repeat it again. So what's the slope going to be here? Well, it's still 1 over x, but my x value now is 3. So my slope here is going to be 1/3. So that means for every step that I take, so as I go from 3 to 4, I'm taking 1 step. As every step that I take, I have to go up 1/3 of a unit. Well, that's a little hard because I'm starting at a half. So I got to add to that like a third, maybe like here. Okay, so it's kind of hard to eyeball it, but it should be something like that. Now it asks me for the precise value. What would that value be? Okay, so I'm at 1.5. I'm at 1.5, and I'm adding to that. I'm going to add to that my slope, which was I'm going up 1/3 of a unit for every step. So I'm going to add 1/3. And fortunately, it's got the little Desmos calculator in here, so I don't even have to pull out my own calculator. And it tells me I'm at 1.833. And yeah, looks like that's pretty much where I eyeballed it. Okay, so explain your thinking. I'll let you do that. You explain my thinking. Okay, but remember, as we move along, our slope is changing because our slope is a function of x. Here's our slope, 1 over x. Our slope changes as x changes. And then also think about this, 1/3 means we go up. We're going up 1/3 each step. So each x unit. So each step. Oops, I've run out of room. So each step to the right, each whole unit to the right, I'm going up 1/3 of a unit. That's a way to think about it. All right, next one, 6. Same thing again, but now we're going to do it a whole bunch of times. So you get the idea here on slide 5, and now we're going to do it a whole bunch of times on slide 6. But instead of taking whole steps, we're going to take half steps. So it's going to get a little bit trickier. So I'll do a couple of these, and then I'll let you do the rest. So at the point 1, 0, our slope is going to be 1. Okay, so you see that dy dx is 1. And our y value, how did our y value change? It went up 0.5 because I am going, the slope is 1. So that means I'm going to go up 1 for every 1 unit to the right. Okay, but I'm not going a whole unit to the right. I'm only going half a unit to the right because I'm stepping over by a half unit. I'm going to 1.5. I'm not going all the way to 2. So that means I'm only going to go up half as far. So I'm going up half of whatever the slope is telling me. I'm going up half a unit. Because if I was going to the right a whole unit, I would go up a whole unit because the slope was 1. But since I'm only going to the right half unit, then I'm only going to go up half as much, which is 0.5. So my y was at 0. It's going up 0.5. So my new y value here, my y1, is equal to 0.5. All right, now the slope here, we're going to have a new slope starting at this point. The slope is going to be 1 over x. So 1 over, and what's our x value here? 1.5. So there's my new slope. So from here, I'm going to go for each step, for each whole step over, I'm going to go up 2/3 of a unit. But I'm not going over an entire step. I'm only going over half a step. So that means my change in y is just going to be half of my slope. So I have 1 divided by 1.5. Oops, I'm sorry. Let's write that over here. 1 divided by 1.5. And then I'm going to take that and I'm going to divide it. Okay, let's see if this will do it. I'm going to divide it by 2. Yes, which is 1/3. Okay, so this is 2/3. Half of 2/3 is 1/3. Okay, I was a little worried that my Desmos calculator was going to get messed up there. So if I had been going over an entire step to the right, then I would have gone up 2/3. But since I'm only going half a step to the right, because my x values are changing by a half unit each time, I'm only going to go up half of that slope, half of that rate of change. So instead of going up 2/3 of a unit, I'm going up 1/3 of a unit. So now I'm going to add that to where I was. I was at 0.5. I'm going to add to that the 1/3 that the slope is adding on to it. So my new y value, when I get to 2, when x is 2, my y value is going to be 0.8333. Okay, here's 0.8, so it's just a little bit above that. Okay, then we're going to do it again. I'm going to have a new slope here. My slope is going to be 1 over x. What's my x value right here? 2. Okay, because my x value right here is 2, so the slope at this point is going to be 1/2. So now that means that for every step to the right, I'm going up half a unit. So for every whole step to the right, I'm going up half a unit. But since I'm only going half a step to the right, I'm going to go half of 0.5. So 0.5 divided by 2 is 1/4, or 0.25. So my change in y, I'm going to add that to my existing y. So my existing y was 0.8333 forever. And I'm going to add to that my 1/4. That will get me my new y value. So 2.5 is going to go up to 1.08. Well, that's close to 1.1. Here's 1.2. 1.1 would be there, more or less. All right, I'm going to let you take it from there. You can do the rest on slide 6. Okay, then they do ask you, after you have all the points on here, you're going to connect your points with straight line segments. So I'm going to use the straight line segment tool to connect my points. And you're going to keep going. All righty. So then on slide 7, they want you to go back. It says, compare the curve you drew on slide 2. You didn't draw one on slide 2. That's a typo. That should say 3. Okay, so you're going to take this one on 6, and you're going to go back and see how does it compare to the one you drew by hand on 3 when you were using the slope field to solve the problem. And you're going to look at the other ones that you did along the way. How is it looking? So really the one that you want to compare to is slide 3 to slide 6. How is it looking? And say, what do you think? What's going on here? All right. Then you can do this, use a calculator. Actually, the calculator is already in here. So you don't have to pull out a calculator. You can just type natural log of 1, and it'll give you some answers. Okay, natural log 1.5, and it'll give you the answer. All right, so you're going to do that. Then you're going to plot these points on the graph. So 1 and 0. And then 1.5 and 0.4055. Okay, so 1.5, 0.4 would be here. So like that. All right. And you're going to keep going. And guess what it's going to look like. All right. And then for the last one, here is the graph of natural log of x. And it's saying that this is a solution to the initial value problem. The derivative dy dx is equal to 1 over x. Now think about, could we solve this problem algebraically? So I want you to think about that. That's what you should be considering in this box here. Explain why or why not. I want you to think about the 3 different ways now that we can solve a differential equation. So we can solve algebraically. So solve this algebraically. What happens? We can use a slope field. See what happens. And we can do Euler's method. This is Euler's method. So that's it for your helper video for Desmos. I will be making a video about Euler's method. Actually, can be condensed down into a formula. So we are going to have notes. There will be a video on notes about the formula, Euler's method, the equation, the formula about Euler's method. So, all right, that's it. Good luck finishing up your Desmos.